Hey everybody, this is Larry. This is day 9 of the Leetcode Daily Challenge. 9th. Hit the like button, hit subscribe button, join me in Discord. Let me know what you think about this one. Today we have 3133 minimum array n. You're given two integers n and x. You have to construct an array of positive integers nums of size n such that for every I, except for the last one I guess, it is greater than the previous number, and the result of the bitwise AND operation between all elements of nums is x. Return the minimum possible value of the biggest number. Okay. I think apparently we're doing bitwise operation the last couple of days, so let's think about this, right? I mean, the way that I would start about this is that they're really how do I say this? Right? Okay, let me read it again first. You have to construct positive integers. They're all bigger, and it's x. The resultant bitwise AND operation between all elements of nums is x. Right? I think the way to think about this is that there are really two ways you can try to think about it, right? You could start with, or to start thinking about it, not that it is the solution. It was what I was going to say anyway, but one is thinking that, okay, we start with the smallest number and then add bigger numbers to it. Or we can start with the biggest number and then add numbers to it, right? Or yeah, add numbers smaller to it. The thing is that with this one, right, we're trying to minimum the biggest number, and it's a little bit awkward. I mean, I know how to do it, I think, but it is still very tricky. So one thing to note is that for bitwise AND of numbers to a series of numbers, say in this case it's an array, but let's start with a series of numbers. And in this case, as is the case with yesterday, let's take a look at the two numbers at a time, right? And the thing is that because if you, and I didn't do this that well yesterday, it was very late, I don't know. So you have like maybe x of 0, x of 1, x of 2, x of 3, right? Something like that, and you want to XOR these numbers. Oh, sorry, I just too used to XOR bitwise AND these numbers, right? But of course in this case there's what's it called? Is distributive? Oh no, it's commutative. No, not commutative. What is the one that is Man, it doesn't matter which order you do them, is what I'm going to say. And as a result of that, you can think about it as like, you have this number, oops, which is just equal to, you can think about it here like this, right, and so forth. And here, this is just like another number, and then you can think about this number like this. So you can just basically put the parentheses wherever, right? And what that effectively does is that you can say this is just another number, right? So you have C, some other number, dot. And what I'm trying to get at with this point is that you can, even though it's a bitwise number of an array, you can focus initially with just two numbers, because everything will be kind of almost like an inductive kind of way, right? Like you start with two numbers, something that becomes, or you find something true about how they interact, and then you could kind of build more on top after that, right? And okay, so yeah, so then now, as we said, we can either start with the biggest number and then go down, or we could start with the smallest number and go up. I think the way that yeah, I mean, you can maybe think about the biggest number, but then it's a little bit tricky because you have a biggest number, you XOR your way down. Oh, sorry, I keep saying XOR, my bad. But you bitwise AND your way down, and you're trying to make sure that the last all the numbers will have bitwise n of x in this case, right? So what does it mean to have a bitwise n of x? Well, the reason why we brought this up is that now we can reduce to just two numbers, a and b, right? Well, a and b is equal to c. What does this mean, right? For some, let's just use x because that's the input. And what does this mean? Well, that means that in a 1 bit by 1 bit scenario, that means that well, you can do the truth table, right? So you can do something like 0 0 0 1 0 0, right? I mean, we know what it is. I'm just writing out anyway, though. So yeah, and that what does this mean? That means that, you know, and for bitwise operation, the way that sometimes I think about it is every digit stack on top of each other, right? Or going from left to right, if you will. But sometimes I think it this way. And what I mean by that is like if you have 15, you have 1 1 1 1. Maybe not. No, that's right. 1 2 4 8, right? Yeah, and then maybe you have like, I don't know, 13, right? And it's you have 1 0 1 1 or something like this. And I guess it doesn't make sense in the way that I did it, but I meant the least significant bit in the first. So this is 2 to the 0, 2 to the 1, right, and so forth, right? Dot dot dot. And here now, so these may be possible A's and B's, but now you have basically you're given x this thing, right? So then you have x is equal to maybe some number, right? Is, I don't know, 1. Just, you know, this is just random, right? It doesn't mean anything. But what that means is that what does this mean, man? That means that both numbers a and b, if you kind of work backwards from it, that means that you know you're forced. You know, at certain positions you're forced, right? Because in this case, if x have a 1 in a bit, then you're forced in those positions to be 1. That means that these have to be 1, right? So these are 1. Okay, we copy and paste. Only because it's so annoying to tap, right? Okay, right? And then here, for the stuff that I didn't fill in, which are the zeros, you can kind of do whatever you need to do, right? And maybe what you need to do, or what you can do in any case, is just that what you can do is just be in a greedy kind of way if you're trying to get the smallest, right? Now you kind of see this, and you try to be small, and then now basically maybe here we can maybe I'll put something for like I don't know, something to denote that this is a choice, right? So maybe I'm lazy, so maybe C, right? And this is C0, C1, C2, whatever it is, right? C sub A0, whatever. And the idea here is that for all these things that we get to choose on, we just do greedy growing up, right? So maybe maybe I'll just leave underscore, right? So that means that, okay, well, if x is equal to and maybe I did this in the wrong order anyway. But so if this is x is this in binary, then now you start with the number where, or you have. That means that you have to try to fill out these blanks, and of course they're prefix blanks as well, right? So then now in a greedy way, you can think, okay, well, you can either the same thing that we talked about, build up from the biggest number and go down, or the smallest number to go up. And for me, I mean, honestly, it seems pretty, at this point, after all the work that we put in, you easily see why in a greedy way, if we go smallest up, it's a little bit easier, right? Because we just throw in all these underscores with 0, right? So then the first number, maybe a sub, whatever, num sub 0, a sub 0, is just equal to this thing, except for that they're all ones, all zeros, right? And then now a sub 1 will be the same thing, except for now we can't do the same thing because it has to be strictly greater than because of the rule. So then we just take the next one. And then a sub 2, we can think about doing the same thing, except for now we do this one, right? And so forth. And that's really the idea about it. I mean, in terms of implementation, this isn't easy, but it's also not super bad. So I think, yeah. I mean, I think there are some cool ways of doing it. But if you just want to remove all those, like one way that I would maybe think about implementing it is just thinking about, okay, well, what does this effectively do? That means that we remove all the ones. Like we just remove this one, remove these two ones. All we have is like all these blanks, and all these blanks we're just trying. If you're trying to go from smallest to greatest, you just kind of from 0 incrementing every time, and then fill in the ones where necessary, right? So I think that's basically what we're gonna do, and you know that's pretty much the idea. I think there's also a cool way that I may or may not work, so I'm gonna play around with it. But yeah, so current is equal to x, and then we have n number. So we have to increment n minus 1 time, I think, because you start with x and that's already one number. And then here we maybe increment by 1. We want to OR it with x. Yeah, and that should be it. Maybe something like that. I don't know. Maybe that's wrong, actually. I don't know. But that's how I have it in my head. Am I good enough to submit? I don't know, actually. Honestly. 0.5. Does it have to be positive? Nope. I mean, the input has to be. I don't know. And for this reason, I think one thing that I would say though is that I think this is kind of a cool way of doing it, but if it's right, and I think this is right anyway. But of course, I now look at the constraints rather, and this is going to be wrong, or it's going to be timeout anyway. Because 10 to the 8, doing 10 to the 8 incrementation is too slow. So you should probably do it the other way, because the other way that I said, we just treat it. If we strip all the ones, we treat it as a number. Because you're just incrementing it whatever times, and then just put the ones back in later, right? So that's really, I guess, the idea that we should go. The reason why this works, and this is kind of cool, is that if you kind of think about it this way, at any number here, you increment, and because everything that is preset, the old ones, if you want to call it that, everything that is going to be 1 when you increment, like if you're going from here, you increment, and there's a carry, all the ones do will just shift it forward, right? So it will help you carry. It doesn't block in any way, which is why you can just do current plus 1. And then OR means that, well, every bit that we shift the preset ones that were turned to zeros, we turn them back to 1. So that's what the bitwise OR does here. And as I said, I mean, so I think this is kind of a cool way of solving it, honestly, but it is going to be too slow, which is fine. We can just do it the other way where, you know, we just have the number, and then we just throw it in, right? So yeah, so then now we have, yeah. So then maybe we have current is equal to n, right? Or n is the number that we're trying to increment it n minus 1 time, right? Maybe increment, right? And then now we just do a bitwise thing, right? So here we look at each digit, or each binary digit, that is. That means that, yeah, if x, and this is maybe looks a little bit funky, but all it does, and you should actually, you know, this is a bit shift, this is a bitwise n. I think that I get a lot of questions sometimes about how to like remember these and all these things. But honestly, I don't always remember. I mean, by now I guess it's muscle memory, so maybe you could say I remember it, but I never thought to memorize it. I only write them out because you think about what you want to do and then do them. And for me, it is about getting the ith bit. And to get the ith bit, I have to shift them to the left, I times, or yeah, and shift of 1 to the left, I times, and then x, we do a bitwise n to see, and then we check to see if that bitwise n result is greater than 0, to see if there's a 1 in the I position of x, right? In any case, if there's an I there, if there's a 1 there, then we always do the I, right? Otherwise, if it's a 0, then we take the smallest, least significant bit of increment. So that means that so maybe it's this times. You could say that it's this bit shift times increment mod 2, right? It's a little bit yucky, probably, and maybe if you want to keep in the bitwise thing, you can say this is n1 or something like this. Basically, it takes the least significant bit, And if this is a 1, then this would be a 1, which allow us to set this to true. And maybe instead, you can even say instead of multiplying, you can maybe just do like a thing, right? You can actually even instead of multiplying, well, or maybe it's still a multiply, but you could just put this inside as part of the thing, right? I don't know, but this is how you end up with code that is unreadable. Maybe you followed me, maybe you didn't, but either way, if you look at it, then it's just unreadable as a result. But in any case, and then now we get rid of the least significant bit by eating it up by right shifting, and that's pretty much it. Yeah. The idea, and yeah, is that 8? I don't know. Yeah, close enough, probably. Yeah, so it looks okay. I mean, it looks like a big enough number, and that's pretty much it. I mean, I should submit before. So what's the complexity? Oh, is it because? Yeah, okay. I was actually thinking about this. I was wondering if this would be enough, but it is more than 32 bits is why. I was just being lazy. I was like, maybe there's a chance, but then I think I was just talking about the bitwise things and I forgot about it. And it actually comes, this is the one time where Python actually like is a little bit tricky, because if you look at another language, it'll tell you that this is a long, which means that, hey, remember this is a long, so you gotta do your things. But in Python, it's just easy to not do it. But yeah, I mean, if you want to not think about it, 64 is fine. It's actually 10 to the 16, I suppose, in the interleaving kind of way, which, I don't know, maybe it's fine. What was the, I guess I might as well actually test this before. But yeah, I was just a little bit lazy. And also the billion thing, I thought I tested, I mean, I did test it, but I guess I got a little bit lucky that this is, it's actually sometimes a little bit surprising that smaller numbers give a bigger result. Anyway, let's go a quick submit. I guess that's why we submit it first. But yeah, what's the complexity here, right? This is going to be linear time, linear space. I mean, this is only 2 times the size of the input. Keep in mind that the size of the input is the number of bits, and for each bit in the input, we do it twice or something. You can maybe even say I squared, which is, I guess, n squared if you want to call it that, which actually I guess technically is true, but I don't know. But yeah, okay, fine, maybe it is quadratic then. But yeah, but you in theory, even one shift is going to be, because you can actually like incrementally shift this one, and maybe that's a little bit better, but not really, because you still do work on all the zeros. It's just, I don't know. But anyway, that's all I have for this one though. Hope you had fun. Thanks for watching. How did this video took 18 minutes? I mean, I don't know. Maybe I was just chatty today. But hope that kind of explains the thought process in general. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.